Hello, how's it going today? If you can turn to page 24 in your packet, we're going to take a look at number 62. All right, so let's just read this together. It says, drugs break down in the human body at different rates and therefore must be prescribed by doctors carefully to prevent complications such as overdosing. The breakdown of a drug is represented by the function, and they give us this function right here. And then they explain what everything means. It says that N of T, which is right here, is the amount left in the body, so the amount of drug left in the body. N sub 0 is the initial dosage. So this is the initial. All right, R is the decay rate. So there's R. And notice there's a negative in front of it, probably because it's decaying. And T is the time in hours. So we have a T right here. Okay, and if you notice, doesn't this kind of look like the APERT formula, right? A equals P E to the R T power. So it's pretty similar. We have the negative because it's decaying. All right, patient A of T, is given 800 milligrams of a drug with a decay rate of 0.347. Patient B of T, is given 400 milligrams of another drug with a decay rate of 0.231. Okay, in part A, they want us to write two functions, A of T and B of T, to represent the breakdown of the respective drug given to each patient. Okay, so I'd like everyone to hit pause, and I'd like you to use this formula, and I'd like you to use what they give you in order to make these two functions, A of T and B of T. And then when you're done, hit play and see how you did. Okay, well, I'm going to start. Here's patient A, and I'm going to underline patient A's information. So we could write A of T equals, okay, so in place of N of T, they wanted us to use A of T. N sub 0 was the initial, so they said initially patient A took 800 milligrams. And then I know they put a parenthesis around the E here. If you want to do that, go for it. If you don't have to. It's the same thing either way. And then I'm going to take this negative sign. And in place of R, right, the decay rate is 0.347. If you prefer to write 0.347, you can. And then I'm going to leave it in terms of T. I'm having trouble making that 4. There we go. So there's patient A. Okay, now patient B, they want us to use B of T for patient B in terms of time. Patient B started off with a 400 milligram dose. Okay, so that's the initial amount. Again, if you want to put the parenthesis here on the E, you can. And then we have a negative exponent. And since the decay rate is 0.231, I'm going to plug that in. And we're going to leave that in terms of T. So there are our two equations. All right, now in part B, they want us to graph each function on the set of axes below. Okay, so I guess let me label like what, let's first label the axes, what each of these axes means. So we can see right here, this little T just represents time. And if you read the problem above, we have to see it's time in terms of what? Minutes, hours, days. So let's move back up here and let's see. So T is the time in hours, okay? So when we go to, and you always want to label your axes when you're graphing something like this. So this is going to be time in hours. Okay, now the y-axis, let me just scroll back up here again. Okay, so the y-axis is going to be represented by whatever N of T stands for. And it says here that N of T is the amount left in the body. So it's basically like the amount of drug that remains in the body. So I'm going to label this axis over here. I'm going to call it, let's see, drug remaining in body. If it's easier for you to write this sideways along your paper, you can. So drug remaining. That's supposed to be an I in there. It's kind of hard to say, in body. And that was, what was that, in milligrams, I believe? If you look back up at the top of the page, yes, it is milligrams. So I'll just write mg. Okay, so now what we're going to do is, I'm not really sure at this point how high to number along the y-axis, or even, along the t-axis. But what we're going to do, actually, you know what? You actually do kind of know how high to number up along the y-axis, because think about this logically, okay? If patient A started with 800 milligrams and the amount of drug is decaying, isn't it going to go down from 800? So 800 is the highest we need along this y-axis. And then 400 was patient B, which is, half the amount that patient A took. So I'm going to actually label the y-axis right now. So really, this axis, we have to label up to 800. So I believe there's 20 boxes here. So I think what I'm going to do is I'm just going to basically like skip a box, right? And label this 100. Skip a box 200. Skip a box 300, and so on. All right, so why don't you guys hit pause, number the y-axis, and then we'll talk about the t-axis. Okay, so the t-axis just represents time in hours. So I'm assuming we're going to need 1 hour, 2 hours, 3 hours. I'm not sure exactly how far we have to go. You know what a good idea would be? I would do this. I would just go to y equals in my calculator, and I would plug this into y1, just use an x instead of a t, and plug this into y2, again, using an x instead of a t. And let's go to our table of values and let's try to see what's going on. And then that'll tell us along, our t-axis, probably how far we need to number. Okay, so in your calculator, you're going to want to go to y equals, like we said, and plug this into y1, and then b of t into y2. Okay, now this is what I decided to do. Rather than changing my window and trying to look at this in my calculator, because to be honest with you, I don't need to actually see the graph in my calculator in order to plot points, right? I need to go to the table of values. So I started out when x was 0, because if we're talking about time, we can't have any negative time anyway. So you'll see at 0, the first graph is at a height of 800, and the second graph was at a height of 400, which we already knew because that was the initial dose. T represents a time in hours. So after 1 hour, patient A has this amount left in his body, whereas patient B has this amount left in his body. Okay, and if you look at the numbers, see how, these are going lower, and these are also going lower because it's decaying. But if you look here, see how Y1, these numbers are bigger than the ones in the column of Y2, but then all of a sudden you get to hour 6, and look at this, Y1 is lower than Y2. So I kept scrolling down the table. I went to hour 7. Y1 is dropping even lower than Y2. At hour 8, look, it's dropping even lower than Y2. So basically what happens is Y1 starts off with a greater initial dose, but because it's decaying at a faster rate than patient B, at some point, patient B is actually going to have more remaining in his body than patient A. So within the graph, really what you want to show is you want to show at least to where these intersect, to where they cross each other. And I would show a little bit past that. So since you could see at hour 6 is where patient B now has a greater dosage than patient A, you want to graph at least to hour 6 along the time axis, along the x-axis. In this case, we're calling it the t-axis. So if I scroll down here, okay, we know along the time axis, we're going to need to at least graph to hour 6. So I think what I'm going to do is I'm going to skip a box, kind of like I did with the y-axis, and I'm going to skip a box and label this 1 hour. Skip another box, 2 hours, and so on. Okay, I know I have to go at least to 6 hours, but I'm going to want to go a little bit more than that just to show what the graphs are doing. Okay, I'm going to go to, let's say, hour 8. That should be good. And then what I'm going to do is I'm going to just plot these points. So for example, let me start with patient A. I'm going to plot the point 0, 800. So I'll go to 0, 800 and plot a point. Okay, there we go. Then I'm going to plot the next point, 1, and I'm going to estimate where I think 565.44 is. So at 1, I'm going to go up to 500. This would be 550. So figure 565.44 would be somewhere around here. Okay, I'm just going to estimate that, and I'm going to put a dot right there. Okay, so I'm going to keep doing that for patient A for, up until I numbered the t-axis to 8, up until 8. So if you could hit pause and do that, that would be great. All right, so here's what my A of t looks like. So now I'm going to do the same thing with B of t, okay? I'm going to plot, so now we're looking at the y2 column, right? So at 0, we're going to go up to 400 and put a point. So 400 right there. Okay, so now we're going to go to 1, and we're going to go up to 317.5 and put a point. So just do your best to judge, 1, if here is 300, and this is 350, figure 317.5 is somewhere down over here. So I'm going to put a point right there. All right, so if you could do this for all the points of B of t, you could hit pause and then hit play when you're done. Okay, so there's my B of t. Now, if you notice for both graphs, I put arrows, right, because they're going to continue on. And I also labeled them so we know which is which. Okay, now I think if you flip to the next page, there's a couple questions that deal with these graphs. So let's check those out. All right, so letter C, to the nearest hour, so we're rounding to the nearest whole number. When does the amount of the given drug remaining in patient B begin to exceed the amount of the given drug remaining in patient A? Okay, so you can either look at your graph from the previous page, or even more specifically, I'm going to take a look at the table of values on my calculator. So if you go back to your calculator and go to second graph, okay, so we actually talked about this just a few minutes ago. If you look at the table of values, okay, this is where I happen to be. So patient A has a greater amount of drug in the body than patient B. Okay, same thing here. This number is higher than this number. At hour 5, patient A still has more drug remaining in the body than patient B. But once we get to hour 6, look at this. The amount of drug remaining in patient A is now lower than the amount of drug remaining in patient B. So hour 6 is when this happened. And they wanted us to round to the nearest hour anyway. So this would be hour 6. So 6 hours. Okay. Okay, so now the final part of this question, letter D. The doctor will allow patient A to take another 800 milligram dose of the drug once only 15% of the original dose is left in the body. Okay, so basically we have to figure out what 15% of 800 is. So we're going to take 15%, 0.15, right? We know to change from a percent to a decimal. We move the decimal place back twice, so 0.15. And we want to find 50% of 800. So that means just multiply 800 by 15%. And when we do, we get 120. Okay, well, let's just go back to the original equation, right? The function a of t was equal to 800 times e to the negative 0.347 t power. So if we want to know to the nearest tenth of an hour how long, right, we're looking for the time it'll take until they're allowed to take another dose. We want to know how long does it take for 120 milligrams to remain in the body? So I'm going to replace this A of t with 120. Okay, we want that to be the amount remaining. So let's replace that with a 120. And then we're just going to solve. Okay, so I'd like you to hit pause, solve this, and then hit play and see how you did. All right, so we know that the base e contains this exponent, this variable exponent on it, so we need to get the e by itself. So let's first divide both sides of the equation by 800. Okay, so 120 divided by 800 brings us to 15.15, right, 15%. And that's going to be equal to e to the negative 0.347 t power. Okay, to get rid of an e, we put an ln in front of it. Okay, so the ln gets rid of the e for us, and it leaves us with negative 0.347 t, right? The exponent just drops right down. And on the left-hand side of the equation, I'm just going to bring down the ln of 0.15. And then to get the t by itself, let's divide both sides of the equation by negative 0.347. So that's going to leave us, oops, sorry about that. That's going to leave us with t being equal to, and we're just going to have to plug this in our calculator. When we do, we get approximately 5.4672. Okay, and they want us to round to the nearest tenth of an hour. So the 6, we'll round that up to a 5, so it'll be 5.5 hours. Okay, and make sure you put your units. Don't just write 5.5 because this is a 5.5 minutes, days, it's hours. So please make sure that you include your units. Okay, so now if everyone can turn to number 63 and just read the question on your own, and then when you're done reading it, just hit play and we'll talk about it. Okay, so basically we're given two different functions here. V of t represents the value in dollars of the car after t years. And then z of t is measured in dollars, and it's the unpaid amount on Zach's loan over time. So what they want us to do is they want us to graph v of t and z of t over this interval where t is between 0 and 5. Okay, so this down here, this is going to be our t-axis, so we have to graph between 0 and 5. So what I'm thinking is that since there's 20 boxes, if we did 20 divided by 5, that would give us 4. So you can jump, you know, every 4 boxes and then put the number 1. So for example, if you did 1, 2, 3, 4 right here, we can put the number 1. Then if you went another 4 boxes, we could put the number 2. And so on all the way until you get to the end. Okay, and this is going to represent time in years. Okay, now along this axis, we're talking about like money, right? The value of the car or the amount of money left on the left on Zach's loan. So I'm just going to label this. I'm literally going to call it dollars. Okay, it's the amount of money in dollars. Or you could put, if you want to say the amount of money and then in parentheses put dollars, just like in here, parentheses, I put years, that's up to you. All right, now, I think what we're going to do is we're going to go to y equals in our calculator, and I'm going to plug this function into y1 and this function into y2. Now, I just want to point something out. When you're figuring out how to label the y-axis, I mean, here's the deal. If you look at this, right, this is the initial amount. And since this number is less than 1, we know our function is going to go down. Same thing over here. This is the initial amount. And in the parentheses, right, it would be like 1 minus the rate. Since this number is less than 1, it means it has to go down. So really the highest we're even going to need, the highest value on our graph is 28,482, which if you want to round up to 30,000, you know, you can do that. So along our y-axis here, okay, if you want to think ahead, if that's hard for you to do, you can always go to y equals first and look at the y values and figure out how high you need to go. But I'm realizing that this is going to be the highest number I'm going to deal with. So if I'm going to label up to 30,000 along my y-axis, how am I going to do that? I think I'm going to jump 5 boxes and label that 10,000. So 1, 2, 3, 4, 5. I'm going to label that 10,000. I'm going to jump 5 more boxes and label that 20,000. And then I'm going to jump 5 more boxes and label that 30,000. And that's where I'm going to stop. Okay, I don't have to go all the way up to the very top of the graph. If I want to, you know, to make my numbers even more exact when I graph them, I can. But to be honest, I think it's going to be a little more confusing to do that because now, think about it. If every 5 boxes gives you 10,000, aren't I going up by 2,000? So this would be 2,000, 4,000, 6,000, 8,000, 10,000. Okay, so that's what I did to make it fit. Now, what we're going to do is, again, we're going to go to y equals in our calculator, and we're going to plug this function into y1, and then we're going to plug this function into y2. Okay, so that's what I did. I went to y equals. You can't see the whole equations here because they don't, you know, fit on the screen. And then I went to my table of values, and I mean, these are the points I'm going to plot for v of t, and then these x values along with the y2 values are what I'm going to plot for z of t. Okay, so let's start with v of t. The first one we're going to plot is 0, and then 28,483. Now that's a total estimate, right? Because think about it. If this is 30,000, this is 2,000 less, this would be 28,000. Figure 28,483 will be a little bit above it right here. Okay, so I'm going to put my first point right here. And it's just going to be an estimate, the best you can do, okay? So this represents the point 0, 28,483. Now I need to graph 1, 19,482. So if I go over to 1, I'm going to go up. I'm just going to estimate, probably right about there. That's where 19,482 would be. Okay, so I'd like you to plot all the rest of the points for v of t. And then when you're done, I'd like you to graph these x values with these y2 values, and that will be z of t. All right, so this is what my graphs look like, and I want to point something out, okay? It says to graph it between 0 and 5. And see how these are underlined? It means you're going to start at 0 and include that point, and you're going to stop at 5 and include that point. Underline means we want to include those points, but you don't want to go any further. So please don't put arrows, okay? Because we want to stop on this domain. This is the domain they give us, between 0 and 5, so we're only going to graph in between 0 and 5. Okay, so we're only going to graph from here to here. All right, so this is our graph. That's it for part A. Okay, the next part says to state when v of t equals z of t to the nearest hundredth and interpret its meaning in the context of the problem. Now, do you remember when you see something like this, if we want to know when they're equal, I mean, I can look up at the graph here, right? And it's going to be where they intersect. But it's hard to tell exactly where that's happening from my sketch because, although I graphed this as accurately as I could, I mean, each box represents $2,000. That's a big span. It's hard to graph those points, exactly. So what we're going to do instead is we're going to use our calculator, okay? We're going to figure out when the first function intersects the second function. Okay, so if you recall, in your calculator, you should still have those functions under y1 and y2. Okay, and what we're going to do is we're going to figure out where they intersect. Now, I am going to change my window so I could see the graph. So I'm going to hit window, and we know the x we did from 0 to 5, right? I mean, you can see that right here on the screen from 0 to 5, right? Now, the y-axis, I'm not going to scroll up, but do you remember we went up to 30,000? So I'm going to make my y-min 0, okay, because we don't use any negatives. And I'm going to make my y-max 30,000. Okay, so there we go. Now that window matches the window on my paper. So I'm going to hit graph. There we go. And if we want to figure out where they intersect, remember in our calculator, we go to second trace. So I'm going to do second trace. And then I'm going to choose choice 5, which is intersect. Okay, let me make this a little bigger so we can see what's going on. Now, you can move your cursor over to the point of intersection a little if you want, but there's really only one of them, so it doesn't matter where your cursor is. But you're going to hit enter 3 times. So you're going to hit enter, enter, enter. And when you do, see right here where it says intersection? Okay, this is the point where they intersect. All right, so we have it here. Here's the point of intersection. Now, if you recall, whenever you see this, when does one function equal another function? Okay, this is telling us that we're looking for the x values only. Or in this case, we're not using x, right? We're using t. So we're looking for the t value of the point of intersection only. Okay, and the reason why, if I were to take v of t, which is this, and set it equal to z of t, which is this. So if I were to solve this equation, see how there's only t's in the equation? Okay, that's why we only care about the t value, which represents x in this case, of the point of intersection. So this is what we care. This is really what's important to us. So they want us to take that, and they want us to round it to the nearest hundredth. Okay, so t is equal to, and this would be 1.95. So that is the answer to this. Now they also say interpret its meaning in the context of the problem. Okay, so what that means is, so t is time. So it takes 1.95 years for v of t to equal z of t. Now if you recall, v of t is the value of the car, and z of t is the unpaid amount on Zach's loan. So it takes 1.95 years for the value of the car to equal the unpaid amount on Zach's loan. So we could just write that out. Okay, so here it is. After 1.95 years, the value of the car is equal to the unpaid amount of Zach's loan. Okay, and then finally the last part. Zach takes out an insurance policy that requires him to pay a $3,000 deductible in case of collision. Zach will cancel the policy when the value of his car equals his deductible. Okay, so we know that v of t represents the value of his car. So let's take v of t, which is 28,482. That's supposed to be an 8.698 to the 0.684 t power. Okay, so we're taking the value of his car, v of t, which we wrote right here, is equal to, so let's put an equal sign, and his deductible. And they told us the deductible is $3,000. So this is the equation we're going to solve. All right, we know that since we're solving for an exponent, we're going to have to use logs. So we have to get this base that contains the exponent by itself first. Why don't you guys try to solve this on your own, and then you can hit pause and, play and see how you did. Okay, so we said the first thing we had to do was we had to get this base to the t power by itself. So we're going to have to get rid of the number in front of it by dividing both sides of the equation by that number. Okay, so we're first dividing both sides of the equation by 28,482.698. All right, so those cancel. So on the left-hand side of the equation, we're left with 0.684 to the t power. If you want to leave that in parentheses, you can, but you don't have to anymore. Now, I'm going to round this. I have to plug this in my calculator. I'm going to round it on my paper to 4 decimal places, giving me 0.1053. But I'm going to remember to use that leave that number on my calculator. I want to use the entire thing, not the rounded version. All right, now that we have this base that contains the variable we're solving for, the variable exponent by itself, now we can put the word log in front of both sides of the equation. Because remember, what that allows us to do is we're allowed to take, it's called the power rule, we're allowed to take the exponent and bring it to the front of the word log. And then that exponent is no longer an exponent, which is what we want, right? Because we want to solve for that exponent. Now, since we have t times log of this decimal, to get the t by itself, let's just divide both sides of the equation by log of 0.684. So in your calculator, you're plugging in what you see on the right-hand side of this equation, right? You're plugging in log of 0.1053 divided by, don't forget to close the parenthesis in your calculator, divided by log of 0.684. And when you do, you get approximately 5.9260. Okay, and they want us to round to the nearest year. So the nearest year, this would round up to 6 years.